Hello everyone, I'm Alessandro Pegoraro, and I will present VoiceRadar, voice deepfake detection using microfrequency and compositional analysis. So, how are we living with deepfake in our lives? Sadly, deepfake audio is well permeated in our life and can be used for fraud, for example, to bypass voice authentication. We are still waiting for the iPhone to activate using only our voice, but sadly, it will not be able to currently because of this deepfake. There is also disinformation, political warfare, political warfare, fake audio of our political enemy could be distributed to make them say things that will be bad publicity. And lastly, audio deepfake could be used for defamation, so character assassination and so on. So we wanted to analyze how easy it is to generate deepfakes. And currently, even big companies have announced or released their own deepfake generation or have made them available to the public. So what is the overall principle for deepfake? We have the victim, original data, original audio, and we have also the target content. So for example, we could use text-to-speech or speech-to-speech. Text-to-speech is more precise, but takes much more time to generate, while speech-to-speech contains more artifacts during generation, but is much more faster to generate and can be used for real-time deepfake, for example, Zoom call and so on. This data is passed to a feature extraction and feature blending, in which characteristics of the data, such as text, for the text, the structure, the word, the language, or the audio, the tone, the pitch, and the pronunciation, are extracted and mixed together, and then forwarded to a multitude of possible deepfakes into this generative AI. And then we obtain our deepfake audio. So this is how deepfake audio is generated. How can we detect it? There are multiple deepfake detectors that we can categorize into three main categories. Detectors that look at uncrafted features, so inherent attributes of the audio files. So for example, there was a paper that analyzed that deepfake audio cannot generate mute audio, so only a real speech could have pauses like this. Instead, a deepfake audio would not be able to generate this. Graph neural network based, in which they represent the audio as a graph and then train a neural network on it. And obviously, the more common deep neural network based, in which represent audio as an encoding. And lastly, there are online tools that are proprietary, and which obviously we cannot know their inner working. And these are some examples of detector in literature. So we decided to evaluate this detector, and as you can see, the blue line represents true positive rate. That is when the detector is able to find a deepfake as a real deepfake, and the red line, the orange line, represents true negative rate. Instead, is the rate at which a detector is able to differentiate a human from a deepfake. As you can see, we analyzed both the text-to-speech domain and the speech-to-speech domain, and we observed that we can never have the best solution, one solution for all, as they have accuracy that is dependent on the domain. They have limited adaptability and generalization, but most important of all, they lack comprehensive audio dataset evaluation. What is? Most of these approaches of this detector that I showed were evaluated only on old dataset of deepfake, like alias spoof audio, while more advanced and proposed application of deepfake generation were not considered. So we decided ourselves to try and find what is the human versus machine difference. And we have our own hypothesis. And our own hypothesis was that human interaction is affected by personal and environmental factors, dependent on individual involved. For example, right now I could be nervous while I'm speaking to this huge public. And for example, there is me, my colleague there, and I want to make a good impression. So the way in which I speak, the way in which I pause myself, the wave move will change. Instead, the machine interaction is fixed. Is evenly dependent on the rule and the pattern that the model in which it is generated has set it for them. So it's less dynamic than human interaction. So we wanted to add a priori information to our dataset and training of our detection model that the previous approach did not consider. So we decided to develop VoiceRadar based on this. So for VoiceRadar, we want to approximate the physical model to represent this a priori information that I just described. So we want to approximate the physical model to simulate the audio wave propagation, how my speech originates and reach the observer, that is you, or the one that needs to decide if I'm real or fake. And to do that, we need to extract the subtle microfrequencies that are then used to differentiate between synthetic audio and real audio. And all of this generates the a priori information that is then incorporated as the compositional bias of our training algorithm for our model, and to penalize mismatch of energies by the model. So overall, we expected to have less energy for machine interaction and more energy for human interaction. So how do we extract and represent this frequency that you observer receive? We employ microfrequencies analysis, that is our embedding, the physical model approximation, there is this detector system that is the observer, and the observer frequency. So this is the high level, but in more low level, we have the we utilize the drumhead vibration representation to represent how of which frequencies my speech is composed, and this represents the frequency of the source, and then we use the Doppler effect to then calculate the frequency of the observer, which is the Doppler effect. And this then is fed to the classical machine learning algorithm. With, in our case, we use binary cross entropy, but other approach, we evaluated also other approach. And obviously, we also have to feed the audio itself for training. And for inference, you can then differentiate between machine and human. So as you can see, the drumhead vibration is composed of three main frequencies. What are these three main frequencies? Those are the translational frequency, that is a simple straight line between me, speaker, and you, observer. There is rotational frequency. So for example, when I'm speaking right now, like this, I could move my hand. When I'm singing, I could move my head. And also the way in which my wave path move. This is causing a rotational frequency shift, like when turning my head. And lastly, speech itself, a subtle vibrational variation, stemming from individual and environmental factors, like we said before. This causes tremor in the speech and does not create a smooth speech. So all of these were incorporated in our approach to generate the Doppler effect and then train the model. So as we said before, the current detector existing literature were lacking in evaluation against existing approach. So we decided to create ourselves our dataset. We created a text-to-speech dataset using the VCT cake dataset for human sample. We used 8 of the most recent TTS approach, and we did the same for speech-to-speech dataset. We then evaluated again our approach, and as you can see, we were able to have an approach that is agnostic to both text-to-speech or speech-to-speech domain. In conclusion, as you can see, Deepfake are a real threat to modern society, and we try to address existing detector limitation, and we propose VoiceRadar that is agnostic to text-to-speech or voice conversion. If you have any question.
Thank you. Thank you. Any questions? So you know how to detect deepfake voice? You want to practice? We have so many audience here. You have tons of questions when you are reviewers, including me, and you mute yourself today. Please come to the front and ask some questions. How did you do the experiment? Right? How many voice did you simulate it?
Oh, can I turn back?
Okay, sorry, I was counting the
yes,
time.
We have on the slide. We evaluated ourselves both on the existing dataset, like IVS spoof and so on, but also we wanted to have an evaluation of existing approach for generating deepfake audio. So this is not the real total. This is just for the new dataset.
Okay, what do you think about the future of this deepfake, right? Or if you think your methods can be applied for video deepfake?
We are also working still with this approach for image deepfakes of frame, But we are dependent, again, in our intuition is dependent on the embedding. So we have to first train an embedding generation.
Great. We have the first question
Thank
from
you.
our audience. Yeah?
Yeah, thank you so much for your talk.
Yes.
I had a question. So some of the features that you're particularly trying to look at, the Doppler effect, drumhead vibrations, are there any particular peculiarities of these features that would make it very hard for a machine learning model to begin to produce itself? Or I guess I'm wondering are these things future-proof to deepfake generators, or would an adaptive adversary?
I understand. We evaluated in the paper adaptive attack, for example. So, for example, we assume that the attacker knows this detector, so tries to project the frequency of the observer such that its audio will have that frequency, and we show that while that is correct, then the audio becomes currently it's more like the current audio generation are not on par to have this adaptive loss, let's say, to also consider this. But maybe future approach would be able to do that.
Okay, yeah, so it requires some fundamental new changes to deepfake generation.
The most important, maybe I didn't want to speak too much, what we use is not classical classification. We use energy-based model that are not as intuitive as classification. In classification, I'm talking about machine learning right now, you have the last layer in which tells you which class has the higher value, obviously, or maybe you use softmax to normalize. In energy-based model, you don't care really much about the last layer that is normalized. You want the lowest value. So it's trying to, you normalize at in the opposite side loss. So that is as different, employ different loss and different optimization algorithm. That's why it's more difficult for a normal classification, because all of these approach are based on transformer and so on, so they use normal optimization. So they should try to normalize the normal classification that tries to maximize with a classification that tries to lower instead, to minimize. So that is a bit difficult.
Thank you.
No problem.
Thank you. Any other questions? Before we invite the second presentation, the speakers? Nope? Okay. Thank you so much.